Hello everyone, welcome to this lecture on operating system. In this session we are going to discuss an important topic from Unit 2 Process Management. Our topic for today is operation on processes. In this lecture we will mainly discuss three important concepts. First, process creation, second, process termination, and third, we will understand the important Unix system calls, namely fork and exec. We'll also see how processes are created in Linux and Windows, and we'll understand concepts such as parent process, child process, zombie process, and orphan process. So let us start with a quick recap of the process concept. In this session, we have five major areas to cover. First, we will quickly recall the process concept. We will understand why processes execute concurrently and why processes needs to be created and deleted dynamically. Second, we will study process creation. Here we will learn about parent and child processes, process identifiers or PIDs, and Linux process tree. Third, we will discuss resources and execution models. We will see how resources and address spaces are handled when a process creates a child process. Fourth, we will study fork and exec. These are very important system calls in Unix and Linux operating system. Finally, we will discuss process creation. This includes cascading termination, zombie processes, and orphan processes. So by the end of this session, you should have a clear understanding of how processes are created, executed, and terminated. Before going into process operations, let us quickly recall what process is. A process is a program that is currently in execution. In modern operating system, multiple processes execute concurrently. But remember, normally a CPU core executes only one instruction stream at a particular instant. Then how do we feel that many programs are running at the same time? The operating system rapidly switches the CPU between different processes. Because these switches happens very quickly, we get the feeling that multiple processes are executing simultaneously. Now during its execution, a process may create another process. The newly created process is called child process. The original process is called the parent process. Similarly, when a process completes its execution, the operating system removes it from the system. Therefore, two fundamental operations are very important. They are process creation and process termination. Now let us understand process creation. During execution, one process may create one or more new processes. The process that creates another process is called the parent process. The newly created process is called the child process. For example, imagine that we have one parent process. This parent creates three child processes. We may call them child A, child B, and child C. Operating system needs a way to uniquely identify every process. For this purpose, every process is assigned a parent identifier, commonly called PID. PID is simply an integer value. For example, a parent may have PID 200, its children may have PIDs 201, 202, and 203. The kernel uses the PID to identify the process and access its associated process information. So, remember, this is important point. Every process has a unique process ID or PID, and processes created by other processes form a hierarchical structure called process tree. Now let us look at the Linux process tree. At the root of the traditional Linux user process hierarchy, we have the init process with the PID number 1. So we can think of init as a root parent of a user process tree. After the system boots, different processes are created. For example, services such as SSH, login services, and other system services may be started. For A user command line shell such as bash can also create additional processes. For example, when a user enters a command, bash may create a process to execute that command. Therefore, the process tree keeps growing depending on the activities performed by the system and the users. The important idea here is that processes are organized hierarchically. A parent can create children, and those children can create further processes. Let us understand this process tree in a little more detail. Once the system is booted, the init process creates or starts various user level processes and services. For example, web server, print servers, and SSH related service may be running. We can also have kernel related helper processes. The SSHT process manages clients that connect to the system through SSH. Similarly, the login process manages users who log in directly. When a user opens a command line interface, the bash shell may be running. From bash, the user can launch programs such as PS or an editor such as Emacs. The PS command is useful for viewing information about active processes. For example, PS space -el can display detailed information about processes. So the main idea from this slide is that the Linux operating system maintains a hierarchical process structure. Now let us discuss an important question. When a child process is created, where does it get the resources required for execution? A child process needs resources such as CPU time, memory, files, and input or output devices. There are two basic possibilities. The first possibility is that the child gets resources directly from the operating system. That means the operating system allocates a new set of resources for the child process. The second possibility is that the child receives a subset of the parent's resources. For example, the child may share or inherit access to certain files or other resources associated with the parent. Why do we restrict the resources of a child? Suppose a parent process creates a very large number of child processes. If every child can freely consume system resources, the system may become overloaded. Therefore, restricting resources can help prevent a single process from creating too much resources demand. The parent can also provide initialization information or input to the child. When a process creates another process, there are two separate decisions we need to understand. The first is the execution model. The second is the address space model. First, consider execution. The parent and child can execute concurrently. In this case, a parent continues executing while the child is also executing. Alternatively, the parent can call wait. When the parent calls wait, it passes until the child or one of its children terminates. Now consider the address space. The child can initially have a duplicate or copy of the parent's program and data. This is commonly associated with the Unix fork model. Another possibility is that the child loads a completely new program into its address space. This is where exec becomes important. So remember, fork creates the process while exec replaces the process's program image with another program. Now we come to one of the most important concepts in this lecture, that is fork and exec system calls. In Unix, the fork system calls creates a new process. The newly created child process initially represents a duplicate execution context of the calling process. After the fork, we have two processes. One is the parent, other is the child. Then the child can call an exec function. The exec operation replaces the child's current program image with another program. For example, the child may execute the /bin/ls program. The parent can call wait and wait for the child to complete. There is one very important point to remember. Fork returns twice. In the child process, it returns 0. In the parent process, it returns the PID of the child. If a process creation fails, it returns a negative value. This return value helps the program determine whether it is executing in the parent or child process. Now let us look at a simple C program using fork. First, we include the required header files. We include a sis/types.h, stdio.h and unistd.h. Then we define the main function. Inside the main function, we declare an integer variable called PID. Next, we call PID equal to fork. This is an important statement. The fork system call asks the operating system to create a new child process. After the fork call, we need to check the value returned by the fork. If the value is less than 0, it means an error has occurred. In that situation, the program prints a message indicating that the fork operation failed. So the first condition is PID less than 0 means the process creation failed. Now let us continue the same example. If PID equal to 0, we are inside the child process. The child executes exec lp within bracket /bin ls, null. This replaces the child's current program image with the ls program. In simple terms, the child process now runs the ls command. Next, consider the else part. This represents the parent process. The parent executes wait of null function. The purpose of wait is to make the parent wait until the child completes. After child finishes, the parent prints child complete. So the complete logic is very simple. If PID is less than 0, there is an error in process creation. If PID is 0, we are in the child. If PID is greater than 0, we are in the parent. After the parent receives the child's PID, this is a very important pattern in Unix process programming. Now let us compare the Unix model with the Windows model. Windows provides a process creation API called create process. Unlike the simple Unix fork model, Windows provides more explicit structures and parameters for creating process. In this example shown here, we include the standard input-output header and the Windows header. Then we declare two important structures. The first one is the start up info. The second one is the process underscore information. These structures contain information required for creating and managing the process. We initialize the structure using zero memory function. Then we call create process function. This function is used to create a new process. So the important point is the Unix commonly uses fork and exec, while Windows provides create process for explicit process creation. Now let us continue the Windows example. The program specified in this example is c:/windows/system32/mspaint.exe. So the newly created process will launch Microsoft Paint. If create process fails, the program prints create process failed. If the process is created successfully, the parent can wait for child using wait for single object function. The parent waits until the child process completes. After that, the program prints child complete. Finally, the program closes the process and the thread handles using close handle. So the major difference to remember in that Windows makes many process creation detail explicit through structure such as startup info and process underscore information. Now let us move to the second major topic, process termination. A process terminates when it finishes its execution or when the operating system terminates it. Some operating system may also enforce rules where a child cannot continue after its parent has terminated. This can lead to a concept called cascade termination. In cascade termination, when a process is terminated, its child may also be terminated. The termination can continue through grandchildren and further descendants. Now let us discuss the wait system call again. Parent can use wait to wait for a child to finish. The call can return information about child's termination and the PID of the terminated child. But what happens if the parent does not call wait? This can result in a zombie process. And if the parent terminates before the child becomes the orphan process. These two concepts are very important. Let us understand them clearly in the next slide. This is an important comparison. First, let us understand a zombie process. A zombie is a child process that has already finished execution, but its parent has not yet called wait to collect its termination information. Therefore, an entry for the process may remain in the process table. A process is not actively executing, but it is still occupies a process table entry and retains its PID until it is reaped. One zombie by itself may not be a serious problem, but if a large number of zombies accumulate, they can consume available process table or PID resources. Now let us see an orphan process. An orphan process is a child whose parent has terminated while the child is still running. The child is then reparented traditionally to the init process which has the PID 1. The system can then ensure that the orphan is properly handled when it is eventually terminates. So remember this simple difference. Zombie, a child has finished but parent has not collected it. Orphan, a parent has finished but child is still running. This discussion is very important for examination as well as the practical understanding of Linux process management. Let us summarize today's lecture. First, process creation. A parent process can create one or more child process. Each process has a unique PID. The process hierarchy forms a process tree with the PID 1 traditionally serving as a root of the user process hierarchy. Second, resources. A child can receive resources directly from the operating system or can receive a restricted subset of the parent's resources. Third, execution model. Parent and child process may execute concurrently. Alternatively, the parent may call wait and wait for the child. The child may initially duplicate the parent's address space and can then use exec to load the new program. Fourth, Unix and Windows. Unix commonly uses combination of fork and exec functions. Windows provides the create process API for process creation. Finally, process termination. Cascading termination can terminate the entire process subtree. If a completed child is not reaped by its parent, it can become a zombie. If a parent terminates while its child continues running, the child becomes an orphan and is reparented. These are the major concepts you should remember from today's session. So with this, we have completed our discussion on operations on processes. In this lecture, we learned about process creation, parent and child process, process identifiers, process resources, execution and address space models, fork and exec functions, Windows create process function, process termination, zombie processes, and orphan processes. I hope you now have a clear understanding of how the operating system creates and manages processes. Now, next section we'll move to the another important topic, process scheduling and context switching. Thank you for listening. Keep learning, keep practicing, and see you in the next lecture. Thank you.